All right, I'm briefly going to talk about what is voltage, what provides energy in our electric circuits. Now, just quickly, if I think about a battery, what's happening inside a battery, Daniel? You can explain. Get your headphones out, by the way. What's happening inside a battery?
A chemical reaction.
A chemical reaction, okay.
Creating power.
Good.
Power, but like voltage and stuff.
So we've got like a chemical energy is being converted into electrical energy, and then that electrical energy has been harnessed in some way to, for example, create light, create motion, depending on the situation. Now, of course, electrons won't move around a circuit unless they are given energy, and that energy, for example, given by a battery. That battery means it's a potential difference. The chemical reactions provide potential energy to the electrons inside it. For example, if I was to hold up a tennis ball and I was just to hold it there, it has a gravitational potential energy due to the fact that Earth has gravity. Earth has gravity. That means that that ball, the moment you let it go, it is going to fall to the ground. It is going to fall to the ground from rest, and it's going to pick up. It's going to increase kinetic energy, okay, moving energy, if you like. Now, of course, we need, so the energy, the potential energy in, or voltage we call it, the electric potential, is can then be converted to the electrons, which of course move through the wire. Now, now this is commonly called the potential difference. So when we say voltage, it's also the potential difference. So the question could say, find what is the potential difference? It's asking you to find that exactly the same thing. So this is commonly called potential difference and is measured in volts. But the thing is that now what would happen in a battery? How could we explain when a battery goes flat? What can you say about the potential difference in a battery? What happens? What can we say about the potential difference of a battery once it goes flat? Yeah, I guess so. You can say that the chemical reactions are no longer occurring. The chemical reactions are no longer occurring means no movement of electrons, no net charges, flow of charges. But I guess, so really we can say that the potential energy or the potential difference would be zero. In other words, when we connect a battery to a circuit, if there's no flow of charges or no difference of charge, then we can say that the battery's effectively gone flat. So now if you have a look over here, this sort of explains that you can see here this lady, she's holding a ball up. She has this gravitational potential energy, and liken that to potential difference. Now, what about a bird standing on a wire? What do you think? Why is a bird standing on a wire perfectly fine? Well, not necessarily. Is there a potential difference between one foot and the other? No, there's not. So if there's no potential difference between one foot and the other, there's obviously not going to be any flow of charge. So what happens if, however, you were to hold on to a power line and somehow touch the ground? What would happen? Yeah, you'd be in a fair bit of trouble. Or you notice that the birds are holding the same wire. What happens if you were to be stupid enough to grab onto two wires, one with one hand, one with the other? You'd have a big potential difference, wouldn't you? Big potential difference means that, yes, absolutely. So for current to flow through the bird on a wire, there would have to be a potential difference between its 2 feet. So effectively, that's why the bird is perfectly fine. We're talking massive voltage, massive current. They used transformers to up the voltage when they transmit power through power lines. Have you heard that word, transformer? Yeah, I know it's a movie as well, but it's also something we'll look at particularly in year 12, transformers. Change the voltage up so to reduce power loss. Okay, and we're going to start getting into power now. But we can actually quantify voltage, and we know that we know that we'll be told that we have a volt. But what does a volt actually mean? A volt actually means 1 joule of energy per coulomb of charge. Okay, so in other words, 1 volt is the same as 1 joule per coulomb of charge. Okay, so we introduce a new formula, a relationship where E is the electrical potential energy in joules, energy per unit of charge in coulombs. Now, so if I had a 9-volt battery, then I have 9 joules of charge per coulomb. Now, just quickly, we discussed, and I won't go through too much further, we discussed in our prac that we measure voltage, when we're measuring voltage using a voltmeter, or we could use a multimeter, then which measures both current and voltage, we have to connect it in series or parallel. Come on, you can shout it out. Series or parallel, measuring voltage. Has to be parallel because you need to find the potential difference between the two. If you connect it in series, you're not going to have a potential difference at all. So it needs to be in parallel with the device. In other words, one out one end and one out the other. Okay, so we can actually measure the difference. So that's a really important thing when we're doing this circuitry. It needs to be done in parallel. This is called connecting the voltmeter in parallel. Voltmeter, where we connect in parallel. Ammeter, the opposite, we connect in series because we need to measure the current, the rate of flow of charge per unit time. Now, we finally get to, now I've introduced you this formula, V equals E on Q. All right, that's all well and good, but what does QE, what was the relationship for current with, it's the rate of flow per unit time. Now, what happens if I rearrange this formula? I can multiply both sides by T here, can't I? I can say that, which gives me Q, the rate of the charge is equal to the current times the time. Now, what happens if I changed this Q for I times T? Well, that's what I'm going to do. So I'm going to rub this out over here, and that is I times T. And then what we can do is we can say that I'm going to, obviously, I want energy by itself. We can say that energy is equal to VI times T, or V times I times T. And energy is provided by the current. And this is actually, we refer to energy and we relate it to work being done. If I'm holding a ball up against gravity, I'm doing work on that ball. Okay? And that work, we sort of would have done that in year 10, I believe. Did you look at work and potential energy at least?
Yeah.
Yes. So I've introduced to you this formula, but it's really just coming from the two formulas we've just been introduced. Well, we've been introduced V equals E on Q, and we know that I equals the rate of current. Now, that being said, we also can say that that we're going to introduce you that power is the rate at which energy is being transformed. Okay, so we can say power equals energy over time. And let's think about what unit would this be? Well, energy is in what unit? That is in joules, isn't it? Joules. And of course, time, our standard unit, would be in seconds. So power is in joules per second. Okay, -1 referring to over there. But that is also, you would have heard of this before, wouldn't you? 1 joule per second is the equivalent of 1 watt. Plural would be watts. You've heard of that, haven't you? Drawing 250 watts of power. Or now, as it turns out though, we have energy is equal to VIT, and we also have P equals to E on T. So let's have a look at E on T. Okay, if I was to divide this side by T and divide the other side by T, I'm going to say that E on T, which is power, is equal to what? VI. And this is, of course, one of the most important ones that we will sort of refer to. So there's that relationship between power, energy, time, voltage as so many joules per coulomb of charge. And you guys will have to do some basic questions. Now, I'm going to pause this and try it yourself. Have a go at this worked example 3.33. So, power is 720 watts. Pretty straightforward example. We have some analogies. Sorry? 720. Yes. What? What? Okay. Now, of course, I think, resistance, we've been through that stuff. So really, we've introduced you the two more things here. We've introduced that the potential difference is energy per how much energy we've provided to each coulomb of charge. That's a very important fact. And without that energy, there's no movement of electrons. There's no electricity. The second thing is that power is the rate at which energy is being transferred, and we have shown you that given what we already have, there is a relationship between voltage, energy, and power, which we can equate to current times voltage, and that is, of course, in watts. What is a watt, though? If I was to say what is a watt, well, if you think about it, energy is in joules, and times in seconds. So 1 joule per second is a watt. 1 joule per second, which of course we can say as represent like so. Now, I'm going to leave it at that. I think you guys should try these questions. Based on what we've done just now, you should be able to have a go at some of those. I'll stop this now so it doesn't go forever.